Okay, so today we're going to be talking about calculus, but what I'm going to talk about more is how that relates to machine learning in the context of gradient descent, which I think is super interesting. By the end of today, hopefully we'll have some understanding of how machine learning as a whole works. I'll be talking about machine learning and gradient descent in the context of a linear regression. So whereas yesterday I talked about linear algebra and how stats models uses the linear algebra method to solve for the coefficients of your linear regression. Today we're going to talk about a different method that scikit-learn actually uses, which is gradient descent. So the two methods to solve linear regression that we would have talked about by today are the linear algebra method, which is like multiplying all those matrices, the transpose, the inverse, all of that. And then the gradient descent method of today as well. So to start, let's do a very, very brief introduction of calculus. So calculus encompasses a lot of things, but for us, the main thing we're going to talk about is a derivative. So out of calculus, we have the definition of a derivative. All right. Are these random spots here. Okay, so a derivative in calculus definition is an instantaneous rate of change. So I think it's very, very important to remember that it is an instantaneous, and where's my pen? Here we go. Instantaneous rate of change. And we'll see why the word instantaneous is extremely, extremely important. Let's talk about derivative in the context of a linear regression to start. So imagine we have our really poorly drawn graph over here, and we have a bunch of data points going along here, 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 here. Let's just say that the y-axis is price, and our x-axis will be square foot. Just as an example, we build our regression model like this, and we end up with a coefficient of $20 for the square foot variable. So coefficient is 20. So if we remember from how we are supposed to interpret our coefficients, a coefficient of 20 means that for every 1 unit increase in square footage, price should go up by 20. So in other terms, let's say we have square footage here. Let's just say this is 100 and the price is, I don't know, 1.2 million. I don't know, that doesn't make sense, but whatever. Let's just say that our price is at 1.2 million. If we go from 100 square foot to 101 square foot, the price would be 1.2 million plus $20. So that's what a coefficient means. And that's where we have rate of change. Now, in linear regression, because it's linear, all of the relationships between each independent variable and the dependent variable are linear. That means that rate of change is constant. So this line that we're drawing is a straight line. So when we go from 100 to 101, it's an increase of $20. When we go from 1000 to 1001, it's also an increase of $20. So that's something that's actually really neat about linear regression. It makes it easy to interpret, easy to explain relationships, because you're just like increase this by 1, no matter where you are in that range, you're going to increase your dependent variable by the coefficient amount exactly. So that's what we mean by the rate of change. 20, this coefficient, oops, that wasn't erased. Okay, so the coefficient of 20 means that the derivative is 20. The rate of change of square foot with respect to price is 20. So technically the derivative of price with respect to square footage is 20. That's one way to think about it. Now, with a straight line is easy to talk about. However, a lot of times you don't have these linear straight line relationships, as you saw in a lot of your EDA. So in other cases, you might have something that looks a little bit more like this. Excuse my poor drawing, but let's say we have square foot again, and we have price. And let's say instead of a linear relationship, perhaps you have a relationship that looks a little bit more like this. Maybe at some point, I don't know, maybe in this range of square footage is over here. It just doesn't make sense. Just a hypothetical scenario, but it is possible to have this kind of relationship where it's not a straight line. And with not a straight line, you actually don't have a constant derivative. Whereas here we had a constant rate of change of 20. Here you can see at some parts, as you increase square foot, there is a greater effect on price. And at some points when you increase square footage, it has a negative or much less of an impact of price. And the way you do that is through looking at instantaneous slopes or instantaneous rates of changes. So for example, let's say up to this point in that range, when you increase your square feet, the price will increase, although not constant. So it's not that, okay, you increase from 100 to 101, it's not always going to be a $20 increment. The increment is going to change. And that's based on the slope at these, at the specific points in this range. So for example, if we look over here, if we, in the way that we do it in math is we sort of like imagine there is a straight line that touches this point over here. That would be our derivative, which is a steeper slope than if we were to compare over here. And we draw a slope over here. So this slope sort of determines the derivative. If your slope is steeper, there is a higher derivative, and if the slope is not as steep, it's a smaller derivative. So as we get from square footage A to square footage B, this price always increases, but increases at a decreasing rate. And if you were to look at this point over here, if we were to draw a line across here, the rate of change is actually flat. So at this specific point B, the instantaneous rate of change of price is actually 0. Any questions about all of this terminology? Cool. So the main thing I want to get across from here is for a lot of different functions and a lot of other relationships, if you were to not fit a linear model, you will have non-constant rates of change, basically non-constant derivatives, which is something that's pretty important when we get to gradient descent. Something else I want to talk about, I mentioned this point over here where the rate of change is 0. That's actually extremely important for when we get to gradient descent. Something that's important to remember is whenever you have some sort of minimum or maximum point, the rate of change is going to be 0. So for example, here, as your price turns from, as your increase in price goes from positive to negative, we have a maximum point here where the derivative is 0, and same here. Oh, why do I keep accidentally erasing? And also over here, when we are over here, you have a flat line. Therefore, the rate of change at that point is also 0. So usually when you have a derivative of 0, it signifies that you have some sort of minimum or maximum, which is going to be useful for us when we get to gradient descent. Cool. Any questions before I move into gradient descent? Okay, this is a super crash course in calculus, by the way.
I have a weird question. I don't know if this is even relevant, but would the first data point closest to A also have a gradient of 0?
Yeah, so, well, I guess in this diagram, there is no line, but let's say we had this line go all the way down here, then it would not have a gradient of 0 because it would just have a gradient of whatever is here. If there's nothing that exists there, you mean like this point, like right at the tip of this line here, like this here?
That's correct.
I think technically it would still not have a gradient of 0 because at that specific time, if this function has like an equation that is related to it, you can still find a non-zero gradient. It'll probably be something like this.
Yeah, so
yeah.
it'll probably be the steepest in this particular example. Okay, got it.
Yeah, that's right. Yeah, gradient 0 is only if it's like a minimum or a maximum, or there's something else known as like an inflection point. That gets to more than we need to know. But if you ever see a graph that looks like that has kind of that shape, I'm drawing it really poorly, but if you have a graph that is this shape, it has a point where the gradient is also 0, and that is neither a minimum or a maximum, but this is not relevant to us right now. But yeah, calculus, as you know, in colleges, they teach it in like 3 parts. And this is pretty much like the first 1.5 parts of calculus, which means like 1.5 semesters worth. So if it's a lot, I totally understand. But hopefully this point of constant versus non-constant derivatives comes across. Constant derivatives is what we dealt with in linear regression, which is how we can explain our coefficients. And non-constant derivatives we'll talk about in the context of gradient descent. Cool. Any other questions? All right, let's delete these. Actually, just delete everything. All right. So when we're talking about gradient descent is literally the process of how most machine learning models learn, which is really, really neat. And with gradient descent, what we're looking at the derivative of is the derivative of a cost function. So every machine learning model that we're going to touch on actually starting tomorrow, going into the next 2 weeks, and linear regression has an associated cost function. So I'm going to just write that down. What we always have is a cost function. So whatever model you're doing has an associated cost function that your model uses to iterate on and improve itself and basically learns from. And yeah, it's directly related to how a machine learning model learns. So what about for linear regression? For linear regression, the cost function that we used was, it actually, like a huge hint is from the name of the stats models model. It's OLS, ordinary least squares. So we're actually looking for the lowest least square error. So how you calculate cost, and which is actually what scikit-learn does when it's trying to fit the model, is given a bunch of data points over here. Let's just say we have some data points. Yeah, those would be our examples. And we build a model over here. Let's just assume that is our linear model. Our cost will just be the sum of squared errors here. So that is how we determine cost. And basically what scikit-learn is doing when we're doing linear regression is it's just testing different lines, not just this blue line. Maybe it tries to fit a line that's more like this to see which one fits the best. If you have the lowest cost, it's a better fitting model. And scikit-learn does this iteratively through the process of gradient descent. So we're going to walk through the process of gradient descent and how it works. So to simplify things, let's just say that this is a square foot predicting price model, just the one variable. When it scales, it actually scales in exactly the same way. I'll talk about some examples in a little bit. And actually, the way that you do it across many different things is in combination with some linear algebra techniques as well. But yeah, so this is our cost function. Our cost function for linear regression is just sum of square error. Okay, so once you know your cost function, the way that gradient descent works is it just starts with some really wrong and off parameters. So let's just get rid of these. Oops, now when I want to erase and draw something. Okay, let's get rid of these markings for now. And let me draw back a couple points. All right, so let's say we have these points over here. Whenever you're starting the process of gradient descent, you actually initialize with some initial parameter values. So let's just say we're trying to find the best coefficient value for this linear model. And as you know, the coefficient determines the steepness of the slope. So here we'll have square foot, we'll have price, that's our price. And we're going to try and figure out what's the best slope. We'll not care about the intercept term first. So we're just going to take our line and start with an initial value. And let's start with an initial value of slope of 0. If a line has a slope of 0, it's actually like flat at 0 the whole time. And what we're going to do is we're going to keep track of what our cost is at. So while we have this on the left side, on the right side, let's keep track of our cost, which here is our sum squares. Sum squares, and in here we're looking at our beta 1. Beta 1 being the coefficient for square foot, or coefficient for square foot. There we go. All right, so when our coefficient for square foot is at 0, which is at this point over here, when the coefficient for square foot is 0, what is our error? Our error is going to be pretty bad, right? It's going to be pretty high because the error is the sum of all of these distances. So with that error, let's just imagine it is something arbitrary up here. So that's what our error is. Currently pretty high. Again, depending on like what the numbers are, it's in context, it's going to be pretty high with this kind of data, because this blue line flat that's on the right side here, on the left side here, this is what we think our model is at our first iteration. So cool. Now we know that this is a pretty bad model, and a couple things we're going to do. At this point, you will have determined some sort of learning rate. This is not something that we saw with our linear regressions while we were doing our project, but going forward, some of the models, you'll see this one parameter called learning rate. And learning rate basically tells your model how much to adjust the parameter value by. How much should I increase or decrease beta to try and improve the model? And so learning rate just determines how much to change the next value of beta. So learning rate, I'll come back to in a little bit, but let's just say, okay, I'm gonna increase my beta 1 by a teeny tiny bit, and I will make this green line that slopes something like, oh, damn, let me undo all that. A green line that slopes something like this. Cool. So now that we have this green line, our beta increased by a tiny bit. Let's just say this green beta is here. And we're going to calculate our cost again. So our cost looks like it's doing a little better. These arrows overall are shorter. So now our cost is a little bit lower. Let's just say that this green X over here is the cost at this point. So we can still do a little better. So what gradient descent is going to do is take into account the learning rate and keep incrementing on different values of this beta 1 to try and get the cost as low as possible. And by the definition of learning rate, as your error gets smaller and smaller, you'll increment by less and less, if that makes sense. So it's not like we're always increasing by an equal amount here. The increments are going to get smaller and smaller because your error is going to get smaller and smaller too. So your next point, let's just say it's yellow. The yellow point maybe will be something like this, and you'll have some error value. And typically you have a cost curve that's going to end up looking something like this, and it'll start to flatten out. And then your x's go like that. And so that's the whole process of gradient descent, because you're using the gradient of your cost curve and you're bringing your gradient down to 0. Because at this starting point, and this is where we come back to derivatives, if we were to turn this into a curve, let's just use this and poorly connect these lines. The gradient of the cost curve at the very start starts out pretty negative and slowly becomes flatter and flatter and goes to 0. And once you're getting to a very, very low cost, because your sum of squares will never be 0, it'll just start to plateau at some point. Once you get your cost curve plateauing is when your model will be like, okay, maybe depending on the model that you're using, sometimes you can say, okay, I just want to do like 10 rounds of gradient descent, or I want to get to a cost value of a certain amount. Again, that really depends on the model itself. But at some point, your model will be good enough. And then that's when you'll stop, and then you'll find out, okay, this is my best value for beta. Any questions about this process?
Is there any reason it starts at 0 rather than at your lowest data point?
By 0, you mean like, why do I start here?
Why does your first iteration start at 0 rather than at your lowest data point?
Good question. So it doesn't always start at 0. Different models and different libraries have different ways of deciding on initial values. For linear regression, I might be wrong, but I believe that for linear regression, it starts off at, actually, I'm not too sure now that I think about it, but I think there's a chance that it actually starts off with this flat line, right at like the average value. And because for linear regression, you know, you're doing both in a bigger linear regression, you're at the same time adjusting your intercept and all of your coefficients. So it's adjusting not just how much it slopes, but how high and low it is. It's doing all of these at the same time, actually. But yeah, it doesn't always have to start at 0. When we get to some more complicated models later on, you'll see that for some models, they initialize at random values. Some models, they initialize at like high and low values. So it's not always 0. Any other questions?
Thank you.
You're welcome. Any other questions?
Yeah. So does the cost function always take this shape? Can it ever be like, you know, something with like multiple relative minimums?
Yeah, absolutely. So that is something that I would say for linear regression doesn't happen too often. And that's actually where I'm about, yeah, it has something to do with learning rate as well. So if you imagine, let's say I set my learning rate way too high. And let's say like the optimal value for beta is here, where I put this blue tick. And if my learning rate is too high, and I try and look at something that's like maybe out here, let's just say I'm looking at this point over here. In that case, my line, and this is going to get really messy, but my line would be something like this, and you're going to have greater errors as well. And so there is a chance that your curve is going to try and self-correct. Typically, it's not like it will have jagged shapes because it usually converges at some point. So if you were to zoom out and look at the cost curve as a whole, it usually looks more like this, and you're trying to find this exact point. But it does sometimes depend on the model and how many parameters you're trying to optimize at the same time. The reason why you see coefficients change when you have just one less variable is because you have to do this process all over again, and then your optimal values might change. But for the most part, most cost functions do have this shape. Yeah.
So if the relative and the absolute minimum are different for a cost function, is it ever possible that because for gradient descent, it's going to go forward if the slope is negative and then backwards if it's positive. Is it ever going to just completely miss the maximum because it thinks the relative minimum is the actual minimum?
Yeah, so in some neural networks, especially, which we're only going to get to in phase 4, unfortunately, neural networks, that's a huge problem because your cost curve does not look just like a simple U.
Right.
But for neural networks, you can have cost curves that look like this. And maybe you have like a true minimum that's like over here. But if you don't set the right initial values or the right learning rate, you might completely miss this, and you might end up picking like maybe one of these minimums instead. We'll kind of see the implications of that. And for something like a neural network, and you'll see in neural networks, we're actually doing like millions of parameters at the same time. That's usually something that you just keep in mind of, unless you're getting into like the real weeds of like machine learning engineering and you want to like really adjust every single little thing. For the most part, if one of your parameters out of like 3 million misses the absolute minimum, is not as big of a deal.
Got it. All right, thank you.
You're welcome. Anything else at this point? Okay, so yeah, actually what I just mentioned is something that I was going to say next about the learning rate, which is learning rate is, I know in your calculus labs, there's a couple labs that have you code gradient descent from scratch, and you get to define like a learning rate. Yeah, if you set your learning rate too big, you can overshoot your minimum. Like you can, as Harrison was mentioning, you could go from here. Why do I keep accidentally deleting this? But you could go from like here to here, and then it slowly like bounces back and forth all the way until it reaches the minimum, which can sometimes be less efficient than you would think, because if you think fast learning rate will learn faster. On the other hand, if your learning rate is too small, it's just gonna take very, very long to get to its minimum point. It'll just take more computational time. In this phase, by this project, you will actually probably hit some models that will take minutes to maybe an hour to run. You'll literally just sit and watch your cell run for an hour. Those are the kind of waiting times that you might see at the end of this phase. So just heads up. So yeah, learning rate is something that we will also be talking about more and more in the context of different models as we get to them in the study groups to come. Cool. So this example is specifically for OLS, for a linear regression. When we are going to talk about our other machine learning models, tomorrow we're actually going to talk about linear regression with regularization. And regularization is basically the term used for combating overfitting. Very, very similar. It's going to be a linear regression, but it has just an additional thing in its cost function, which we'll talk about tomorrow, that will help to combat overfitting. Some of your models have overfitting. I know not all of you did, but we're going to talk about linear regression with a different cost function that helps overfitting. And we'll talk about that tomorrow as well. For next week, all of the models that we'll be talking about, I think all except for one, maybe two, I forget what models we're going to be talking about, but almost every model has its associated cost function and has a different method of learning. So what our task is at the end of this phase is we're going to be solving one single problem with a bunch of different models and comparing to see which model does best at solving our problem. So yeah, another thing that I wanted to say is for our project, I don't think we saw, I believe for most of our data sets, we didn't see a big difference in the computational time that it took between the stats model and the scikit-learn model, mainly because our data sets were, I think, all under about 20,000 rows, which sounds like a lot, but in the context of data science, it's not really. So there wasn't a big computational time difference between the two. However, as we saw with linear algebra yesterday, and I kind of mentioned, that process does not scale very well. You imagine the amount of matrix multiplication you'll have to do when you have like millions of rows and hundreds of columns. By the end of this course, you will likely be doing a project with like thousands of columns. So get ready for that. But yeah, that method does not scale well. I've run stats model cells that take like maybe half an hour to run, and it does not scale well. Gradient descent, though, is a process that scales better because just when you have a larger data set, the amount of computation doesn't increase as much as it would if you were to do matrix multiplication. So gradient descent is a process that scales very well. That's something that's also good to know. But yeah, I'm super excited because we're going to be talking about a bunch of different cost functions for a bunch of different models that are coming up in the next 2 weeks. Something that I also want to preface, I'm going to send out a couple resources and add them to our homeroom because I know all of us here have different levels of propensity to understand math. Math is extremely daunting to some, easy for others. I studied math in college, so for me, I like to go into the math of things, but honestly, it is not realistic for all of you to understand the math behind every single model we're going to talk about over the next week. I'll tell you myself, like when I was going through this program, by the end of it, I maybe only understood like 20% of the math of what we were doing because it does get pretty intense. I'll do my best to explain it in as layman's terms as possible, but I'm going to send out a couple of resources and video playlists for you all that will help to simplify and understand to the level that you need to understand for this course. And what I did actually, after I graduated, I did an additional machine learning course just because I wanted to go through the math of it all. Because during this time, this really fast-paced course, there is no time to get into all of that. So I really want to set that expectation that you're not expected to fully understand how each thing works completely. So yeah, I do want to set that expectation, but I'll be adding some resources to your homeroom and also I'll put them on Slack. All right. Any other questions regarding gradient descent? This is pretty much how most machine learning models learn. For those of you who are like familiar with calculus, I remember when I found out that like machines learn through like a first derivative, I felt pretty ripped off, but I now find it pretty elegant. I don't know. But yeah, machines learn through like a first derivative. But yeah, that's kind of all I had to share for today. Does anyone have any other questions? Cool. As mentioned, next week when we start getting into all of our models, I'm going to be giving everybody like a mini assignment that's really going to help with your project. So look out for that. What I'm going to have you do is I'm just going to have you all each write a function and send it to me so that I can check it that you're going to be using in your projects to automate your modeling process. Some of you did that for this phase 2 project, which great job for those who did. If you didn't, that's fine. Not a priority for this last project. But yeah, just look out for that. I'm going to have you all write some functions in next week. Cool. Final questions before we call it for the day? All right. Well, you all have a good rest of your day, and I will see you all back here tomorrow. We're going to hit our first model that, at least now, we're going to hit the first model that we have context of gradient descent for. Cool. Well, don't forget to schedule your project reviews. I think everyone here has almost. I don't know. Well, don't forget to schedule your project reviews if you haven't yet, and I'll talk to y'all tomorrow. Bye, everybody.